Hey everybody. See, the concept of hybridization was introduced by Pauling and Slater. Uh, it mainly emphasizes on the understanding of nature of covalent bonds. We know what is sigma and pi bonds. It's about mainly emphasizing on sigma bonds. Okay, so we hybridization concept does not help us realize how the pi bonds are, what is the nature of pi bonds. Its main emphasis is to understand sigma bonds. Through sigma bonds, it will help us judge the geometry of the molecule, how the number of bond pairs are present, where are the sigma bonds located. Next, hybridized orbitals are being made out of intermixing of atomic orbitals. So, which means if we have s orbital, a p orbital, and so on, those orbitals are the ones which will intermix to give some new hybridized orbitals. Okay. And the ratio would be like this: for every two atomic orbitals, you'll get two hybridized orbitals. For every n number of atomic orbitals, you'll get n number of hybridized orbitals. Okay. So first, let us understand the table that how many number of hybridized orbitals are being involved. Starting with, if you have two atomic orbitals, one s and one p, and imagine both of them are from the same shell. In that case, we say that the steric number is 2 and the shape which it forms. Okay. What are the shapes we have? It has this p orbital and s orbital like this. These two will mix with each other. These two will mix with each other to give a new shape of orbital. So that will be, got it. After mixing these two, you will get a new orbital like this. So which is more elongated. Sorry, I'll write down in a slant form so that it can represent the same form here. So it is like the same slant orbital goes like this with a smaller portion here. So basically, after mixing, what is happening here is one, this is the kind of lobe, one lobe is forming, and this is the second lobe which is forming. And these two, if you mix with each other like this, right? So this is what has been forming. So this is the new set of hybridized orbital. Okay. So for every orbital, if I shade this as the positive side, or I can say which belongs to the same phase here. So this is the orbital which has one particular phase. And then it is like we have a phase of plus and plus, the other one will be minus and minus. So whatever inside here is minus and minus, and here it is plus and plus. So this is how the hybridized orbital will look like. And what is the shape with respect to the center to the to the directions of the lobes? You need to check what is the angle it is making, 180 degrees. So that means it is a linear shape like this. So it is a linear shape which is making an angle of 180 degrees. It is very similar concept what we derived, what we used in VSCPR theory. So shape is linear. The shape is linear. Okay. Now look into this case when you have NS, NP, and NP. Three of them are mixed. If three of them are mixed, that means I have one p orbital, another p orbital, and one s orbital. After mixing all these three, now you'll get a hybridized orbital like this and extended orbital like this with smaller lobes here. Okay. So the shaded ones are the ones which will be ensuring the bonding form, bonding nature. Okay. How does the shape look like? You can see the bond, the angle between them is approximately 120 degrees. So it appears like triagonal planar. So it is a triagonal planar form. Okay. I request if you have the notes, keep writing simultaneously. Okay. Next, if you have four atomic orbitals involved, one s and three p orbitals, we say the steric number is the number of atomic orbitals used. So we have a total of four. So these four, as you mix, so we will get the shapes like this. So we'll have one and two and three, and then this one. So all four of them after mixing, will form into like this, something like this. So the smaller part will be away here this way. Now this is a tetrahedral shape. So it will form a tetrahedral shape. Okay. Next, in case if you have 5, where is sp3 and one d orbital is also been added with it. So I'm directly writing this one. So imagine as if we have, you know, sp3 orbital is like this, and that I'm mixing with another d orbital. You know which d orbital I'll be mixing? I'll be mixing dz orbital. So this is dz square. Okay. So it is like sp3 is been mixed with dz square. On doing so, the dz square will get more elongated. So it will start elongated in this direction. The other 3 orbital would be this way. Okay. So now you can see this will form an elongated orbital, correct? Which also justifies the Bend's rule, which we have learned in VSCPR theory, that on the axial direction it should be more elongated. And this is triagonal bipyramidal. Triagonal bipyramidal. Okay.
So can
Next,
you explain the second one again?
second one, this one.
Yeah,
Okay. So imagine like this. If you have this as the x-axis, this as the y-axis, okay?
yeah.
And one p orbital, which is in x direction, let's say it is this way,
Okay, so the second one's in y direction.
y direction.
Yeah,
And
okay.
then we have s orbital here, okay? Now
Yeah,
mixing of these three will convert into new set of orbitals, which I'll write in different color, which is like this way, okay?
okay.
Clear?
Yeah.
Right. Next, here DSP3. So basically, this is a similar tetrahedral form first. First, sp3 is mixed. On mixing sp3, we'll get this tetrahedral form. And then we are mixing which type of D? We are mixing dz square, which is inner orbital. So it is still the same. So it is still the same here. So whether it is inner orbital or outer orbital does not make any difference. This is dz square here, and this is sp3 here. So you will get a same shape and same geometry as well. Okay, trigonal bipyramidal. Now just be careful with this term, that when I'm using n, it is like we have sorry, this 3 I will remove. So yeah, we have ns. That means if you have fourth orbital, let's say 4s, 4p, and 4d. But here it is 3d, 4s, and 4p. So the combination is like that. Next, sp3d2. So now what we are doing, we are basically mixing. First, we got a tetrahedral here by mixing sp3. This is sp3. And then we have two types of d orbitals here. So one, which is like this. Second one, which is dx square. Dx square, if you recall, it will be along the x-axis and y-axis. So imagine if this is along x-axis and y-axis. So then this is dz square, and this is dx square minus y square, right? And this is sp3. So we are mixing these three orbitals. On mixing these three orbitals, the set of new orbitals which you will get will be this way. So it will be elongated, on one plane, square plane, and two lobes will be up and down. So it is like you can see a square plane forming here. Okay. You can see it is like a square plane forming here. And over the square plane, we have one lobe above, and below we have one lobe. So it is like an octahedron. Got it? So what it is forming is an octahedron here. So like this. So the geometry what you are getting is octahedral geometry. Right. Next, 6. In case if you have 6, 6 as in you get the same octahedral form on which you are adding one more orbital. So let me first put the octahedral orbital. This is sp3d2. This is dsp3. So first let me put the octahedral here. Like this, we have an octahedral above and below. And then we are also mixing, you know, sorry. This is the same form basically, but let me delete this. Yeah, it is the same form, just that we are using inner orbitals, n minus 1, n minus 1. Earlier we use outer orbitals. So the idea would be exactly same. This way. Okay. Next, seventh one, sp3d3. In case of sp3d3, what I'm doing is first I'm taking this octahedral form, and on the octahedral form, right, on this octahedral form, basically now we are trying to add up with dxy. Where would be dxy observed? If you have a molecule like this is how you'll get dxy. On mixing these two, now what would happen? This square plane will become a trigonal pentagonal here, like this way. And one would be up, one lobe will be up, and one lobe will be down, little elongated form. So now you can see, if you check out all the lobes here, we have total 7 lobes. 1, 2, 3, 4, 5, and this is 6 and 7. So what is this one? The hybridization is sp3d3, and name is pentagonal bipyramidal. Pentagonal bipyramidal. Next, if you have dsp2, dsp2 is a very special type of hybridization. It is noticed when you have dx square minus y square. So check out, if this is x and y here, d orbital would be along the axis here like this. Okay, so this is d x square minus y square, and then you're mixing this with sp2. Sp2 would be like this. This is sp2. On mixing these two, what would happen? The orbital gets elongated because everything is on the same plane. It will get elongated, and this is the orbital which you will see, which is a square plane. That's it. So it is simply dsp2 and appears square planar. These are the most common hybridizations which you will come across. All right. So please check them quickly. If you have any doubt, you can ask me.
Could you just explain the difference between the sixth and the seventh one?
Sixth and seventh one is only difference is in terms of uh, size of the orbitals. Okay. But the shape would remain the same, because 3D versus 4D, if you notice, they would have relatively, 3D would have relatively smaller size, 4D will have bigger size. That's it. Okay. But the shape, everything will look same.
Okay.
Clear?
Yeah. Wait, 3D will have a bigger size, right?
Smaller size, beta.
Sorry, sorry, sorry.
Higher orbitals will always have bigger size.
Yeah.
Sir, can you explain the ninth one again?
Ninth one. Yeah. Ninth one is a special case where you have dx square minus y square, which is along the x and y axis, like this. And that you are mixing with an orbital which is present in x and y only. This is on an xy plane. This entire thing is an xy plane. Okay. So this is an xy plane. So
So
on the same xy plane, these two orbitals are intermixing with each other. After mixing, this entire thing will squeeze inside and elongate in all these four directions, and this is how it will become. Got it?
Yes, sir.
so could you just zoom out? I have not written the first four, the shapes of the first.
What?
Could you just zoom out? I have not written the first four
Yes, sorry.
shapes.
Please check.
Yeah.
All okay? Shall we go ahead? Done. Let's go ahead. Now let's see. If our objective is to just find out what is the hybridization, okay? Our objective is to find out what is the hybridization, okay? Check. Let's see. If my objective is to find the hybridization of beryllium, boron, carbon, and this carbon in all these cases, correct? What I will do, simply I will use this formula. Steric number H is equal to half of valence electrons of the central atom minus monovalent molecules, monovalent species. Monovalent means which will make only single correction like H, OH, fluorine, chlorine, bromine, iodine, cyanide, methyl, PH2, NH2, acetate, HCO2. All of them are making only single correction connections. They will only be connected by one bond. So those are monovalent species. So M is number of monovalent species minus Q. Q is any charge if at all present on the molecule. For in this case, BCl2 has zero charge. For example, if at all I have to calculate it for beryllium, so what would I do? H will be equal to half of, okay, beryllium has two valence electrons at two bond pairs, two monovalent elements here. So 2. So 2 signifies it is sp hybridized because Steric factor 2 means sp, steric factor 3 means sp2, 4 means sp3, and so on. Similarly here, steric number is half of, okay, boron is 3 plus 3, so that makes it 3, which is sp2 hybridized. Carbon dioxide, we have half of, carbon has 4, carbon has 4 valence electrons plus 0 monovalent. There is no monovalent. Oxygen is a divalent. So that makes it only 2. So 2 means it is sp. Carbonate. In the case of carbonate here, so carbon has 4 plus monovalent is 0 and minus of minus 2. So whatever negative charge is there, you will add, positive charge you will subtract. So half into 6, which makes it 3. So which makes carbon is sp2 hybridized. Okay. This is the simplest way you can figure out first hybridization on any central atom given. Guys, clear? So for any species is given, this is the first thing you will do. Done?
So 1 second.
Yeah.
So why 4 plus 0 minus 1 minus 2?
Huh?
I've written 4. So what have you written for the CO3 2 minus?
CO3 2 minus 0. Monovalent elements are 0. Oxygen is a divalent.
Yeah.
Oxygen will always demand for 2 connections. And minus of minus 2 because charge is minus 2. Q is minus 2.
Okay,
So
it's minus.
hmm. Okay.
Yeah, yeah. Yeah, I'm done.
Done. Check out. See, I've already discussed this. This is about SP, SP2, okay, SP and SP2. Now, let's come to the second one. If I have to calculate the uh, hybridization for all the central atoms in this case, that is nitrogens. So, what are all the terms we should know? Check out. Valence electrons for nitrogen is 5. Monovalent elements 3. Charge 0. Here, valence electrons 5. Monovalent 4. Charge is plus 1. Valence electrons 5. Monovalent 2. Charge is minus 1. Valence electrons 5. Monovalent 0. Charge is minus 1. Right? So steric number is half of 5 plus 3. 8 by 2, which is 4 which signifies it is sp3 hybridized. Okay. Next, nitrogen. Here, steric number, half of, you know, uh, 5 plus 4 minus 1, again 8, so which is 8 by 2 is 4, sp3 hybridized. Steric number, half 5 plus 2 minus of minus 1, again 4, which is sp3. Steric number, half, this is 5 plus 0 minus 1, 6, so that makes it 3, which is sp2. So you got sp3, 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 and sp2. These are the hybridizations which we got. Now let me tell you one by one how you need to assess how many bondings we have, how many lone pairs we have, and so on. First, check out this one. There are 4 connections. The steric number is like connections. Okay, there are 4 connections or 4 orbitals which you generated, or hybridized orbitals. But there are only 3 monovalent elements, which means 3 were used for bonding, and 1 would be a hybridized orbital but with a lone pair. Okay, so remember that you just need to check out this versus this difference. Okay, so therefore 3 bond pairs we have and 1 lone pair we have. Okay, this is a conclusion you need to make. Check out. Same is the case here. We have 4 and 4 here. So what I can say, there are 4 bond pairs and 0 lone pairs. Come to this side also. sp3. Now notice this, we have 4 but only 2 connections, which means we have how many? 2 bond pairs and 2 lone pairs. Last here, in this case, 3 and 3. So 3 bond pairs and 0 lone pairs. So we have 0 lone pairs. Clear? For every molecule, this is the first thing we need to figure out. What is hybridization and what is number of lone pairs and bond pairs. Now, what does this mean? Check out. How is this got hybridized? Nitrogen's configuration is 2s2 and 2p3. Now, I want to make a hybridized orbital which has 3 bond pairs to be accommodated and 1 lone pair should be present, which means we have 2 electrons here and we have 3 electrons here. So first I will make one of this electron to migrate from this to this one. On migration from 2s to 2p, actually migration is not required also. Okay, even if you do not show migration, that is fine, because you have to anyway mix all 4 of them. So imagine I'm mixing all 4 of them. Okay, so when you mix all 4 of them, I will get a set of 4 new orbitals like this, in which one would be lone pair, the other 3 will be single electrons. So all of these mixed orbitals are sp3 hybridized orbitals. So which is, this is sp3, this is sp3, this is sp3 hybridized orbital, and this is also sp3 hybridized orbital. So if I put all the hybridized orbitals together, how does the shape look like? Like this, like this, and like this. And all of them will have at least one electron here, and this lobe will have a pair of electrons. This lobe will have a pair of electrons, and this lobe, now this is the sp3 hybridized orbital of nitrogen, which is being combined with 3 hydrogens. Each hydrogen will have single electron, and after combining with them, now you will get the final bonded orbitals here like this. Here we will have hydrogen making a bond here, here, and here, and that lone pair will remain like that. Here it will become a bond pair. Here also it will become a bond pair, and bond pair. So you will have 3 bond pairs and one lone pair. Okay, so it appears like we have nitrogen with three bond pairs here, H, H, and H, with one lone pair here. So remember, lone pair is present in sp3 hybridized orbital. And this is a sigma bond. I told you hybridization is all about sigma bonds. So this sigma bond overlap is between sp3 and s overlapping. So all of these sigma bonds are sp3 and s overlapped sigma bonds. Please go through it once quickly. Check if you have a doubt. Right, shall we go ahead?
So just 2 minutes.
Yeah.
Sir,
Ah,
here why aren't we taking 1s2 into consideration? Like why only 2s2
1
and
is
2p?
2 is not the outermost orbit. See, the bonding is always a subject to outermost orbits. Got it? Inertial orbitals are already at a stable form and they cannot be used as long as outermost orbitals are present. Okay? Outermost electrons are present. Okay. And how many number of hydrogens you are expecting to accommodate? Only three hydrogens, right? So for three hydrogens, we require three unpaired electrons, which are already fetching it from the outermost orbit only. Okay.
Yeah, sir.
Hmm. Now, when it comes to NH4 plus, NH4 plus, there are only four bond pairs. So you can see nitrogen's configuration is 2s2, 2p3. So which means we have two electrons here and three electrons here. But the charge here is N plus, which means it has one electron lost. So as it loses out, so which means now we have only one electron in S and three electrons in P. So this is 2S and 2P. Now mix all of them. After mixing, you will get a set of new four orbitals, and each orbital will have one electron, and all of them are sp3 hybridized orbital. Hence, we will have an orbital like this, which has been made by mixing, where each one will have one electron. And this, if I accommodate with four s orbitals from hydrogen, so now you will get an overlapping like this. This is the overlapping I'll get. Okay. So that's the reason why NH4 plus is tetrahedral. It is completely tetrahedral shape. But what about earlier here? What was the shape which you are finding it here? This one is a pyramidal shape because when it comes to shape, we do not count the lone pairs. We only count the bonded pairs. So this is pyramidal shape. So ammonia is pyramidal, ammonium is tetrahedral. Okay. Next, check out NH2 minus. NH2 minus, the hybridization wise, everything is same here. Up to this part, it is same. Okay. Then we have NH2 minus this time. Minus means you are adding how many electrons? One electron. So you add one more electron from, external source, you are getting one more electron here. Now mix them. Okay, this would be 4 now. N minus means 4. After mixing, you will get set of 4 new orbitals, in which 2 will have lone pairs and 2 will have single electrons. And these single electrons are sufficient enough to react with 2 hydrogens here to make this into orbitals like this, where we have overlapping here and overlapping here. Here you will have a pair, here you will have a pair. No? So basically it is like this: nitrogen with a lone pair, nitrogen with a lone pair, and 2 bonded pairs. Shape wise, you have to only look up to this part. So this looks like a V shape. So it is a bent V shape. Bent V shape. Okay. Now check. This orbital is sp3 hybridized, and the sigma bond which is forming here is between sp3 and s overlap. sp3 and s overlap. Okay. Please check all three cases. If you still have any issues anywhere, you can ask me. Nitya, did you get this beta?
Yes, so
Manav, any doubt?
No, sir.
Right. Note NO3 minus. Check out NO3 minus. In the case of NO3 minus, what's happening? Well, nitrogen has 2s2 and 2p3 originally. Now it has become N minus. So it has become 2s2 and 2p4. Okay. So it has 2 electrons in S and 4 electrons in P. Okay, like this, 4 electrons in P. Okay.
Yeah, so I had a question in the NH4 plus. So the 2s, why isn't it completely filled?
2s, why is it not?
Completely filled. It only has one electron. No?
Because N plus is forming means it has lost one electron. So I've removed that from S.
Oh, okay.
Why only S is because I require 4 unpaired electrons as 4 hydrogens are incoming. Okay.
Yeah.
Okay. Now listen up. Here, in this case, it becomes, have you noticed something? That there are 3 oxygens coming, but it appears like I have only 2 unpaired in this arrangement, which means it is not the nitrogen which is taking the electrons. Keep that in mind. So it is not the nitrogen which is taking, those extra electrons which is appearing are actually going into oxygen. So therefore, here the orbital set is pretty much the same here. So this is how the orbital setting would be. Correct. And now notice this one. I have to mix because I have to accommodate 3 bonds here. I have to mix all 4 of them here. Right? Because, sorry, all these 3 of them here. Because then I can make 3 orbitals. So after mixing this, that is 1s and 2p, I will get an sp2 hybridized orbital. In an sp2 hybridized orbital, I will have a lone pair present, a single electron, and another single electron on nitrogen with a square planar, a trigonal planar geometry. And for this, now you are adding how many? 3 oxygens. And you know that 3 oxygens will only make a, because hybridization is all about sigma bonds. So I'll have to express sigma bonds. So check this out. Like this here. Uh, I'll put it this way. Like this. This is p orbital. this is the hybridized orbital, and oxygen will bond with a p orbital because oxygen's unpaired electrons are in p. This is the sigma bond which is forming. So there are three sigma bonds forming here, correct? Okay. And now is the interesting part. There is one more single electron present. So how do we represent that? That single electron is present in an unhybridized orbital here like this. And one of the oxygen will also have an unhybridized orbital probably. This is how it is present. Got it? So now notice this one. In this case, okay. So what is the type of bond which is forming at this center here? So this is sigma bond which is forming between sp2 hybridized nitrogen and p orbital of oxygen. Okay. And then there is a single electron here, and oxygen will also have a single electron. And these two single electrons which are parallel to each other will start making a pi bond. Okay. So after the sigma bond has been made, the leftover electron here, which is in a pure p orbital, this is only pure p orbital. So it is pure p orbital. That would make a pi bond with the oxygen's pure p orbital. Okay. Now if I write the skeleton for that, it is like this. N having one bond here, N having one bond here, one bond on this side, oxygen, and a double bond here. Why double bond? Out of which one is sigma and the other one is pi bond. And what is the sigma overlapping? I've already expressed it here. How's the sigma overlapping is observed. Got it? Now, another important thing what we need to notice here is between these two oxygens, have you noticed something? I had actually two unpaired and one lone pair. Actually, is this a lone pair? Not lone pair anymore because that pair is being treated. I mean, that pair is been making a bond with the other oxygen and forming a coordinate covalent bond like this. So it is only shared by nitrogen and it is not shared by oxygen. So that's why this pair is now involved as a bonding orbital, which is shared only by nitrogen. And now you might say, sir, but what about this oxygen? Oxygen has got only one bond. Go back here. Have you noticed that it has minus charge on it? That minus charge will be taken care by this oxygen to complete its octet. Okay, now the octet is also completed. That is, oxygen has now got one extra electron from outer source. I'll write it in a different color. This is from outer source. Okay, and now this has three pairs here, and then it is bonding with nitrogen like this. And here we have one pair here which is completely coming out only from nitrogen, and here we have, correct, double bond with oxygen which has two lone pairs like this. Now you can see octet is completed because these two electrons and these two electrons, this will complete the octet of nitrogen. So nitrogen's octet is completed. And if I overlap here, so that will make the oxygen's octet completed. This oxygen's octet completed. And here this oxygen's octet is also completed. So this is how the bond will be formed. So what all we had here? We had three sigma bonds where we saw it is sp2 and p overlap. Okay. We found one pi bond between p and p orbital. I found one coordinate covalent bond. Coordinate covalent bond between nitrogen and oxygen, where nitrogen is a donor. Okay. So understand from the basic points, check out if you have got the entire picture of NO3 minus.
So,
Yes, beta.
can you explain from where you said nitrogen won't take the electron, oxygen will?
Nitrogen won't take. Okay. What I'm saying is, when you had this negative charge, you could have two thoughts that why can't this negative charge means one extra electron? That extra electron is going into nitrogen. Now check this out. What if nitrogen, which was originally 2s2 and 2p3 here, correct? In case if at all it takes one extra electron, it will become 2s2 and 2p4. If it is 2s2 and 2p4, there are two electrons here, and four electrons would be like this, correct, beta? Now you have only two unpaired electrons, isn't it? But you have to make bonding with three oxygens, okay? And also oxygens octet, if you need to complete, we need to complete their pi bonds also. Pi bonds के लिए और कोई इलेक्ट्रॉन बचा नहीं है ना?
Yes, sir.
Now you might think, sir, why are we not doing like this? ये तीनों को हाइब्रिडाइज कर दे. चलो s को यहां से एक इलेक्ट्रॉन यहां पे डाल देंगे, दोनों को हाइब्रिडाइज कर देंगे. बट देन यू विल हैव अ p ऑर्बिटल विद अ पेयर. पेयर इज नॉट रिक्वायर्ड नाउ. हमको अनपेड इलेक्ट्रॉन चाहिए ताकि मैं पाई बॉन्ड बना सकूं. So that means these electrons will not go on nitrogen, rather they will go on oxygen. Or or simple way beta, which is more electronegative between nitrogen and oxygen? Oxygen. So oxygen के पास इलेक्ट्रॉन जाना ज्यादा बेहतर होगा ना? Okay,
Yes, sir.
right. All good, everybody?
So 1 second, guys, write down.
Yeah.
Yeah,
Done. Right. Now let's quickly, right? We don't have to, you know, uh, keep on bisecting every other aspect now. In simple shortcuts, how we can solve every other aspect which is asked. That is hybridization, expected geometry, shape, bond pairs, lone pairs, nature of bonding, everything. Now let's see one by one. We'll try to mark. First thing is steric number, that you know how to do it. Please work out simultaneously. So steric number, half of chlorine valence electrons are 7. There are no monovalent elements. There is only one charge which is -1. So 8 by 2, 4, which makes it sp3 hybridized. This much we know. And I told you that always check out this number versus this number. How many we have? 2. 4 is to 2, which means for every 4 orbitals, there are only 2 orbitals covered or occupied by bonded electrons. So other 2 must be lone pairs. So I can say 2 bond pairs and 2 lone pairs. 2 bond pairs and 2 lone pairs here. A negative charge should always go on oxygen, so there is no problem there. And if you notice the bonding kind, chlorine will have 2 electrons in 3s, and it will have 5 electrons in 3p. This is the configuration of chlorine, outermost configuration. Okay. Now I need to ensure that we should have at least uh, two bond pairs and two lone pairs, correct? But have you noticed if I have to make two connections with oxygen, it doesn't seem like I have an extra pair of, extra single electron. I have only one single electron. So here is a catch. So what we can do in such cases, correct? Because when it comes to chlorine, now I know that there is 3D which is empty. 3D is empty now, isn't it? 3D orbital is empty. So what will I do? One electron from 3s, I will jump it to 3D. Okay. After I jump it to 3D, one second. Right, check out, sorry. So one of the electrons from 3s has to be pushed to 3D. So after pushing it, now you will get one electron here. And you see, this should have same 5 electrons. Or I'll do one thing. I'll put the unpaired form here just for an understanding like this. Okay. Sorry, two electrons here. Yeah. And then we have 3D getting one electron in it. This way, okay. But I am supposed to use only s and p orbitals to make sp3 hybridization as per the question. As per the calculation, we got sp3. So if it is sp3, that means I am supposed to have two lone pairs and two bond pairs. So you can clearly notice that two lone pairs and two bond pairs, because single electrons will convert into bond pairs. Therefore, I will have something like chlorine having lone pair, and two bonds here, correct? And two bonds with oxygen. Okay. One bond I can make it as minus because there is one extra minus. And now notice, have you seen that this oxygen does not have an extra minus, right? So where would it get the second bonding? Because here it is getting compensated by an extra electron, but this oxygen does not have. In that case, it has to make a pi bond. So it there's no other alternative but to make a pi bond. But now tell me, chlorine S and P are completely engaged. Okay, they are busy. So in that case, the only option left for us is 3D. So 3p, 3D, sorry, 3s and 3p, they got busy with hybridization. So 3D is only left right now. Okay, 1 second. Right. So 3D would have it. So that 3D would make a pi bond here. So therefore, this pi bond which you will get is d pi and p pi, because d pi is coming from chlorine, p pi is coming from oxygen. And the sigma bonds which you are making is between sp3 and p. This sigma bond is also sp3 and p. And these lone pairs are in sp3 hybridized orbital. Okay, so please check this out. And shape is decided only on the basis of bond pairs. How does it look like now? You can see it is a bent V shape. So the shape is bent V. Shape is bent V. Okay, and what else I asked? Bond pairs and lone pairs, I told you already. There are two bond pairs, two lone pairs. Expected geometry is tetrahedral. Okay, so expected geometry is tetrahedral. But shape, due to lone pairs, the shape converts into bent V. Okay, please check. If you have a doubt, let me know. ClO3 minus. In the case of ClO3 minus, what we could do, steric number, okay, steric number is half of 7 plus 0 minus of minus 1. So which makes it 4, and that is sp3. So if it is sp3, if it is sp3, what do we get? We have how many bond pairs and lone pairs? Just check it out. 4 connections, right? 4 orbitals, but only 3 connections. So which means one lone pair must be present, and uh, 3 bond pairs must be present. And since it is sp3, whatever the pi bond which has been made on oxygens, that has to be d pi p pi only, because those electrons will be in d pi only. So now I'm directly writing it. Okay, one case I've explained. So now I can directly write this. So check out. So we will have one oxygen with a single electron, I mean with a minus charge, and two other oxygens will make double bond. So like this, Cl with a lone pair and one double bond O, another double bond O, and another one with O minus. All good? So check, this pi bond is between d pi and p pi, d pi p pi. Same goes here, d pi and p pi, and this is sigma bond. Got it? This sigma bond is between sp3 and p. In fact, all of these sigma bonds are sp3 and p, and the lone pair is in sp3. Okay, this is a very standard JEE advanced question, because number of compounds will be given and you will be asked how many number of d pi p pi bonds are present. Okay, so for example, if I ask you ClO2 minus, answer is 1, ClO3 minus 2, ClO4 minus, you can guess it, 3. ठीक है, चलो अभी करो. Cl, watch this way I worked for ClO4 minus. Do the same thing for ClO4 minus. ClO3 minus I worked out. Do the same thing here. Now one thing you got to notice here is, because of the lone pair present here, because of the lone pair present here, the shape would be like this. Correct? It is a pyramidal. So shape is pyramidal. Expected geometry. Expected geometry is tetrahedral. Expected geometry is tetrahedral. Okay. So check out ClO4 minus. Quick. ClO4 minus. Done. Any answers, guys? Dave, first give me hybridization beta.
Yes, 4 sp3.
sp3. Very good. And how many bond pairs? How many lone pairs?
4 bond pairs, 0 lone pairs.
Very good. Okay. What about the shape? Because there are no lone pairs, so it will retain the geometry, correct? So shape and geometry, both of them would be tetrahedral. Okay. So it is Cl. We'll have this as double bond O, double bond O, double bond O, and O minus. Correct. So all the pi bonds which you are getting, these pi bonds, what are those pi bonds? Tell me. सारे के सारे डी पाई पी पाई है. And all the sigma bonds which are being made, they are between sp3 and p. Am I right? All good, guys? Check KClO3. KClO3 is basically, first you convert that into ionic form, K plus and ClO3 minus. Since it is ClO3 minus, you can just fetch all the information from the above. It is the same thing. So H is 4, it is sp3, 1 lone pair and 3 bond pairs. Correct? Geometry will be Cl, double bond O, sorry, one will be lone pair, mm, double bond O and O minus. Got it? And shape is pyramidal. Geometry is tetrahedral expected. Now, in the case of Cl2O7, I'll explain this one. Cl2O7, basically we have chlorine with an oxygen at the center, and rest bonds are like this. Now what I'm doing now, guys, imagine I've given you the structure, then you should be able to guess what might be happening. ध्यान से देखो. If I give you the structure already, Cl2O7, है ना? Notice with the chlorine, right? How many number of bonds around it we have? Count it. 2, 4, 6, 1, 7. Total 7. Since there are 7 bonds, that means all the 7 electrons of chlorine are involved here. So there is no chance of having lone pairs. So definitely there are no lone pairs. And how many single bonds you have? That means the first bonds. First bonds as in there is one bond here, one bond here, one bond here, and one bond here. These 4 are sigma bonds. And then there is one bond here, one bond here, and one bond here. These 3 are pi bonds. So how many sigma bonds it has? 4 sigma bonds. 4 sigma bonds on a center is again same as expressing as sp3 hybridization. Okay. Similarly, this chlorine will also be sp3 hybridization. 4 sigma bonds. And how many pi bonds we have? There is one pi bond here, pi bond, pi bond, pi bond, pi bond, and pi bond. 6 pi bonds in total. So 6 pi bonds. Now, can I say that because all of the p orbitals, here also p orbitals are saturated, here also p orbitals are saturated. There is no more p orbital left. So the pi bond has to form only from d orbitals. So all 6 pi bonds has to be d pi and d pi and p pi bonds, because oxygen has unpaired electron in p only, and chlorine now has unpaired electron in d. That's why it is going to be d pi p pi bonds. Okay. So geometry is different always with respect to one center, not two centers. Okay. So with respect to this center, it is tetrahedral because there is no lone pair. Hybridization, the geometry and shape will be same. Here also it is tetrahedral. So in case if the shape, if the uh, bond structure is given, that is skeleton of the molecule is given, then also you should be able to guess what is the hybridization, number of lone pairs, number of bond pairs, type of pi bonds, type of overlapping. Okay. Now let me write down type of overlapping also. If you take any sigma bond, that sigma bond is an overlap between sp3 and p overlap. All good? Kapil, Manav, any doubt?
No, sir, just need to write this down.
No, sir, no, no.
Sorry, for Ditya, answer me the hybridization for all these three beta. Work out ClF3, ClF5, and Cl3 minus. Okay, guys, let's answer now. Starting with the first one. Steric number. Nitya, what did you get? Nitya, are you there?
So I'm still doing it. I had to go and have medicine.
हाँ ओके बेटा चलो फिनिश करो एंड टेल मी. Good. So it is 7 plus 3. That makes it 5. And 5 replicates sp3d. Right, beta? Tell me bond pairs.
Um, SP cube D square.
Yeah. No, sp3d. Only d. Because 5 are there, no, beta?
Yes, so.
And then what is the number of bond pairs? Check out this. If you have 5, I'm expected to have 3 connections. So those 3 connections are bond pairs, okay?
Yeah.
Lone pairs are the difference of those two. So how many?
So 2
2.
lone pairs.
Correct. So 2 lone pairs. So sp3d, out of which 2 of them are lone pairs. Now let's put Bend's rule into perspective. Bend's rule. According to Bend's rule, when hybridization is sp3d, correct? Keep lone pairs, lone pairs on equatorial position, and bond pairs, bond pairs along axial positions, usually as much as you can. Okay. So in that sense, now if you notice, we have chlorine. I'm supposed to have total 5 connections like this, out of which these two will now become lone pairs. Like this, these two will become lone pairs. The rest of the 3 will become fluorine connections. This way. Okay. And the type of sigma bond here, is sp3d and p type of overlapping. And if you remember this one, we discussed in VSCPR theory, if you come across this kind of a geometry here, this lone pair will repel from this end, this lone pair will repel from this end, and make the molecule slightly bent. So you will have like this. Now you will have fluorine, fluorine, another fluorine. We have lone pair and lone pair. So how does it look like, beta? It is like a T shape or an arrow shape like this. So what do we call it? Bent T shape. So the shape is bent T. The expected geometry is trigonal bipyramidal. It's trigonal bipyramidal, but it is bent T shape. Guys, clear? They answer me all the details of CLF5 beta. Work out and let me know.
Two.
6. I'm writing directly. Steric number is 6. Perfect. Then
SP3D2.
very good. So that makes it sp3d2. Hmm? How many bond pairs? How many lone pairs?
5 bond pairs and 1 lone pair.
5 bond pairs, 1 lone pair. Very good. Okay. So geometry, what do we expect this to form? We expect this to form octahedral, na beta? 6 matlab octahedral. This is how you expect. Correct?
Yes, sir.
So Bend's rule is not applicable on octahedral forms. So place first all the fluorines, and then the one place where there is no fluorine, that must be the lone pair. Yeah? So this should have been the shape. Clear? So how does it convert into, what is the shape you will get? because this lone pair will push it from the down here. So it will have slight bent over here. So it will not exactly be uh, planar. Okay, right. So it will lose out the planarity a little bit, but still you call it as a square planar shape. Sorry, square pyramidal shape. Expected geometry is octahedral. Okay, finished. Next is Cl3 minus. Cl3 minus make one as the central atom, the other two as the side atoms, and then overall charge is minus. Okay, use this logic and calculate. Okay, Kapil, give me an idea, beta. What is the
Uh,
hybridization?
sure, so 7 minus 2 and then plus 1, right? So that's
Does it mean
6 by
correct number?
2, that's 3. That's 3.
Check again. 7 minus 2 or plus 2?
Minus,
No, no. Monovalent atoms should be added.
yeah, oh, plus 2, sorry. 7 plus
Hmm.
2, minus of
Hmm.
minus 1.
Hmm.
So
Makes it
that's 10, 5, 5.
5.
Yeah, 5.
Hmm. 5.
Yeah, 5 squared.
So 5 is
5 is,
sp3d.
yeah,
Hmm. Hmm.
yeah, SP3D.
Right. So sp3d. So sp3d as in how many bond pairs, how many lone pairs?
3 bond pair, 2 bond,
3 or 2?
2 bond
2
pairs
bond
and
pairs and
3
lone pairs are
lone pairs, 3 lone pairs.
3. Right. Since it is sp3d, correct?
Yeah.
Okay. We would be expecting, since it is sp3d, we would be expecting to apply Bend's rule. So according to Bend's rule, so chlorine, and we are expected to have this 5 different
Yeah.
positions like this. Okay.
Right.
Out of that, where do we put the lone pairs?
On the left, like,
On the equatorial position. So which makes it one lone pair here,
yeah.
one lone pair here, and one lone pair here. Okay. And rest of the two positions are chlorates. And overall, you can put it as minus charge. Okay.
Yeah.
Okay. So how does the shape look like? Shape you only need to take bond pairs. So it looks linear. So the shape is linear. Okay. Geometry is trigonal bipyramidal.
5.
Please check. Done. Everybody finished? Hmm. Right, Mano? Just give me an idea about these cases, beta. PF3, PCl5, POCl3, and uh, PO2Cl. First, give me hybridization for all the cases.
The first ones are 4.
Give me the number. Mano, straight number.
Yes, yes. So 4.
4. Very good. So it is 4, which makes it sp3.
Yes.
Right? So it is sp3. So if it's sp3, how many bond pairs? How many lone pairs?
So 3 bond pairs and 1 lone pair.
Very good. Right? So which means if at all I keep phosphorus, I'll make 1 lone pair and 3 bonded pairs like this. Correct? And so now the shape, because you are keeping it like this, it appears like a pyramid. So it is pyramidal shape. Okay? Pyramidal shape. The expected geometry is tetrahedral. Okay? But the shape is pyramidal because of lone pairs, right? Okay. Ditya, tell me about PCl5 beta. Steric number.
Um,
How
so
much? How much? 4 or 5?
5.
5. So 5, which makes it what hybridization?
Oh,
sp3d.
yeah.
Correct? So since it is sp3d, bond pairs are how many?
5 and 0 lone pairs.
Very good. So lone pairs are 0. Great job. So now we have P, and then we have so then we have 3 chlorines here, and 1 chlorine up, and 1 chlorine down. Like this. So this is how it will be. So no lone pairs. So shape and geometry would be same, and it will be retained. So shape or geometry will be triagonal bipyramidal. Okay, right. Next, Dev POCl3.
So 4,
4. Steric number is 4. Hybridization is sp3.
SP3,
So how many bond pairs? How many lone pairs?
3 and 1.
How come? 4 atoms है, 4 connections है ना? 4 orbitals है, 4 connections है. So are there any lone pairs beta?
Yes, no lone pairs.
No
4
lone
bond
pairs.
pairs.
So lone pairs 0, bond pairs 4,
4,
right?
yeah.
So phosphorus we get double bond O, chlorine, chlorine, and chlorine. Okay, because it is maintaining its, no lone pair status means geometry or shape would be same, and that will be tetrahedral. Tetrahedral. Okay. Acha, just give me an idea about what type of pi bond this is, beta. What type of pi bond it is? Dave, what type of pi bond it is, beta? Can I say it is d pi p pi, everybody?
How?
Because out of sp3, is there any orbital left? P is saturated. P
Yeah.
to bacha nahi hai. But still you
Yeah.
have to accommodate a pi bond. So where do we get that pi bond from?
You're like shifting one electron from the
Yes,
A
from
to
D.
the D.
Out of the 5 electrons of phosphorus, 4 would be used for bonding. One we would push it to d orbital so that it can make a d pi p pi orbital, d pi p pi overlapping.
Okay.
Are you clear?
Yeah, that makes sense.
Yes, sir.
Right. Kapil, how about POCl, PO2Cl?
So I got hybridization is 3, sp2, and
sp2.
yeah, and bond pairs is 3. Shape will come as linear, and even the expected geometry is linear.
It will be linear or
No, sorry, not linear, trigonal planar.
triangular planar, right? So
Yeah.
it will be like P double bond O, double bond O, and one Cl. So it would appear like a plane like this, trigonal planar,
Yeah, and same geometry.
right? So therefore, this pi bonds would be again which type of pi bond?
So D pi and P pi.
One, can you notice that there is one p orbital still left? It is not completely saturated.
Yeah,
So इसका मतलब one I can use it as p pi, okay, and one I can make it as d
D.
pi, okay.
Huh.
Okay. So the shape is triagonal
Yeah.
planar.
Yeah.
Triangular planar. Okay. Chalo guys, I'll give you another 10 minutes, another 2 minutes. Sorry, 2 minutes. Try the rest, next 4. Quick. Let's go one by one. First, H steric number. In this case, how much? Everybody, let's do it quickly.
Oh,
4 sp3, right?
yeah.
So we would get this as 4 connections here like this. Okay. So overall, it will have a plus charge on it. Okay. Shape and geometry
That
would
right.
be tetrahedral. Tetrahedral. Next, PCl6 minus. So it will be P and Cl. So we'll have like Cl this way. So all it will be minus. All right, PCl6 minus. So what is the shape? What is the hybridization?
6 and the shape is octahedral.
Correct. So 6 sp3 d2, and it is octahedral.
Yeah. So
Very
when
good.
does the other case come when it's D to wait a minute.
Coordination compounds, not in this topic.
D to SP. D to
Not in
SP.
this topic. Yeah. We'll come across that. In inorganic, we'll come across that. In coordination compounds.
Okay.
Hmm.
Like how do you identify when it's this and that?
We have a separate science for it. Don't worry. Okay.
Yeah.
That's not just by simple hybridization. Okay.
Yeah. Okay.
Right. So PO4 3 minus. Steric number again 4 sp3. Did you all get that?
Yes, sir.
Right. So that makes it P with one double bond O. Rest will be O minus, O minus, and O minus. So now because P is saturated, this pi has to be d pi p pi. Okay. And based on the hybridization, the shape or geometry has to be tetrahedral. Next. HPO3 2 minus. Okay. Right. So what did we get as H here? Again 4 sp3. Okay. Check it out. So we have P with one double bond O and one OH. See, usually no, H is not directly connected to the central atom beta. In most cases, it will be connected via uh, oxygen. But in this case, especially in these two cases, थोड़े से structure ध्यान रखना. H3PO2. H3PO2 structure would be P double bond O. One will be OH. The other two hydrogens are directly connected. Okay, this you have to mug up. Okay, you just need to know it. That's all. So H3PO3, P double bond O, H, OH, and OH. Next, if it is H3PO4, in that case, it will be like P double bond O, OH, OH, and OH, like this. This is the cases. Clear? Now, it is HPO3 2 minus, which means two of these hydrogens have gone. So, this hydrogen and this hydrogen has gone. So, what is the shape like now? I mean, what is the structure like now? So, one hydrogen will still be there. The other two will be O minus and O minus. Okay? So, keep this in mind. Okay. So, shape of this one, and shape of this one, H3PO4. It will make it very easy for solving. So now you can see the hybridization would be sp3. Okay. So the hybridization is sp3, which is tetrahedral. Tetrahedral. Okay. And only one pi bond is present, and that pi has to be d pi p pi. Done. So got next one, pH4 plus. Done. So next, let's see pH4 plus. pH4 plus, same as the earlier one. I'll just copy that. This one. This is same as this one. Only thing is, instead of chlorine, now we have hydrogen. Next, PCH3, 2 and F3. Okay, Ditya, what is the hybridization beta in this 10th case? Check.
So the hybridization is 5.
Very good. Hybridization is 5. That makes it sp3d. Okay. So if it's 5, so we should have P, and fluorine should be on the axial direction. Methyl should be on the equatorial direction.
There are two, only two methyl, no?
Hmm?
Two methyl, no?
Or beta? Ah, sorry, two methyls. One will be fluorine. Yeah. Okay. So what is the geometry or shape? Both of them will be same. So that is going to be trigonal bipyramidal. Trigonal bipyramidal. Okay. Check.
So can you explain the eighth one again?
Eighth one. Okay. Eighth one. What I'm saying, when it comes to phosphoric acids, hydrogens in these two cases are directly connected also. Like in these two cases, H, H, H here. But H3PO4, all of them are connected via oxygen. Now, this is an H3PO2 minus. You know where that this 2 minus will come from? 2 minus will come from that acidic hydrogens, which is this one. This is an acidic hydrogen, which means it's sufficiently polarized. I mean, it has high positive charge to release out as H plus. Same goes with this one. After removal of those two H plus only, then we get this point, get this form HPO3 2 minus. Clear there? So that's what we have written it.
Yes, sir.
Okay,
Yes, sir.
right, right, guys. Okay, now you have these things to work out. All xenon compounds. I would suggest all of you to work out first xenon compounds, and then predict the hybridization of these cases which I have written it here. Okay, clear? So tomorrow, please complete that before tomorrow itself. Tomorrow I'll take up all the organic compound hybridizations and then we'll start with bond parameters. Got it? So for now, I would suggest you guys to complete up to this structure based hybridization cases. Okay. Sorry, here, not structure based up to this. Right, guys? So, once again.